We were studying air pollution in Ulaanbaatar, Mongolia. I was a Peace Corps volunteer in 1993 to 1995 there. So I lived there for 2 years, and a lot's changed, and that's sort of my connection to this problem. Uh, One of the things that we're doing two different papers on this. So one is a standard research paper, but let's see here. We have a problem with our introductory course in CIS. We talked about this a little bit earlier, that a lot of the students are checked out during the pandemic and they seem to not like the problems. It's very simple problems. They don't like problems that are focused on a particular major, because we're teaching like a gen ed course, which can have many different majors in it. And I'm from the computer information sciences department, so we teach introduction to computing. And it can be a problem if we kind of have problems that are based towards math or engineering or something like that. So we were looking for a problem that might be interesting to students, and we thought air pollution, because it affects everybody, and it is a huge problem in the world, that this would be a good thing that we could focus on. Our students can come at this problem from many different angles. They don't have to be a math major to participate. They can talk about it from a political standpoint, from a health standpoint, from an environmental standpoint, and just as a equity standpoint for people. So that's sort of the background. That's why we were doing this as a case study for teaching. And just a real quick background on Mongolia. It's a city, it's the capital city of Mongolia. It has about half the population of the country there. The whole country is about twice the size of Texas, but it only has a little bit more than 3 million people. So this one city has roughly half the population of the country. And it's grown tremendously in the last 30 years. So when I first went there, it had about 600,000 people, and now it's 1.6 million people. So it's grown incredibly. Now, Mongolia, for those who don't know, is a very cold country. It's in Siberia. It's below zero for probably about, I want to say, 6 months of the year. And it can easily get to minus 30 or minus 40 degrees below zero. And unfortunately, or just is that Mongolia is a big producer of coal, and it's their #1 source of energy. So they have huge coal plants which heat the city. And that can be a real problem because the city was not designed for 1.6 million people. It was really designed as a Soviet city for only about 500,000 people. The entire city is surrounded by mountains as well, so it's in a valley, and air just does not circulate very well. So this is what it looks like in summer. This is the picture here. Here's what Ulaanbaatar looks like in winter. So as you can see, when it's winter and the coal plants are burning, and all the 1.6 million people are trying to heat their homes, you can get a huge amount of pollution. This PM 2.5, that's a standard measure of pollution. It's very small particles. So it's 2.5 microns or smaller, which people can inhale, and it goes into your lungs, and it causes all kinds of respiratory and heart problems. The healthy level would be less than 50, and during winter, it can easily get into the several hundred. levels, several hundred micrograms per cubic meter, which is a huge amount. Just to show you one of the reasons why this particular problem is interesting, you can see here that the mean amount of pollution is 169 micrograms per cubic meter, but the standard deviation is 171, which is the reason why that's interesting, or at least for teaching students, is that they can't use a normal distribution, right? Like if you try to take 3 standard deviations below the mean, you would have negative pollution, which of course can't happen. So it's a nice problem in that it's a non-normal distribution, and the maximum amount of pollution is just off the charts. It's extraordinarily hazardous. In fact, the US Embassy, which is the agency that started tracking pollution in Mongolia, they consider hazardous to be 250 micrograms per cubic meter, and as you can see, it's well over that. It's beyond. It's just off the charts. They don't even really have a term for anything over 500 micrograms per cubic meter. So that's sort of the problem. And one of the interesting things is that I'll just skip ahead here. Here's the data over time. And as you can see, it's very seasonal, which is another reason why we like this problem for teaching students. As you can see in the wintertime, you have just incredible levels of pollution, particularly right around January. And in the summertime, it can get to levels which are not hazardous anyway. So we're seeing a lot of just unhealthy for sensitive people in the summertime. But as you can see, quite a bit of the year is spent above this red line, which means it's in the hazardous territory. Now, most of the research that's been done on this has been done based on the mean, and saying, oh, well, the mean is 169 micrograms, but it's kind of, as you can see from the chart, it's kind of misleading because during winter, the mean is far higher. And there are all kinds of health problems from that. So, for example, there are many spontaneous abortions in winter compared to summertime. A lot of people die of strokes or heart attacks, particularly during winter. And again, it's just the stress that's on the body. The children that live in the city in Ulaanbaatar have lung capacities which are less than children who live in the country by a significant factor, which is some of the items I have in my notes, but I won't go through them. So we decided to take a different take on it. We decided that we would use extreme value analysis, which if you're not familiar with it, instead of looking at the mean, you look at the maximums. So you're trying to fit the maximum levels of pollution rather than just the mean. So, for example, here we have some data. These are just 3 particular days in December. I just chose them for no particular reason other just to illustrate what happens during the day. And you can see that during the night, things come down, but around about 10 o'clock to noon in the morning, where people are going to work and driving around and turning on the heat in their houses and so forth, you have a spike, which then falls off after lunch. And then during the evening, when people are home and they're cooking and they're, again, heating their houses, you have another spike. And this is in part due to how the winds are blowing on that particular day. So you can see, for example, on 12/2 in the evening, there wasn't much pollution, but that's most likely because there was a pretty good breeze blowing through the valley on that particular day. Whereas on 12/3, you see that most of the pollution was at night. So this is, some good variation in the day. You see that it does come down at some points during the day to very low levels, but then it will spike. And in order to get around that, that was actually messing up our modeling. We used declustering, which I won't really go into it. It's just instead of worrying about every point that goes, every maximum point during the day, you only choose points which are like a new maximum. So for example, we wouldn't count both of these points on 12/1, we would only count the top one. Because basically the atmospheric conditions during that time period were the same, and it was leading to this maximum. In any case, we thought this gave us a lot of stuff that students could explore. This data is online. It is measured hourly by the US Embassy, so they can download it in real time. And just recently, we've been able to model it. So this is sort of what we're looking at now. These are the QQ plots and the probability plots. And you can see in this bottom corner here, this is the fit we're getting for the extreme value distribution. So it's a pretty good fit. And I guess the important takeaway, again, this is not really the focus of this talk, because we're really focusing on a teaching case here for this talk. But if you notice this bottom graph, the dots, the curve is curving down these data points. That seems to indicate that the pollution is coming under control. So this is a return level plot, meaning that you would expect this level of pollution once in the next 50 years. So this is the data we're looking on, and we're trying to come up with ways to make it an interesting case study for students to study in a entry-level gen ed course. So that's really all I have today. We were looking for any input you might have on what we could do to make it interesting, or approaches you might think would be good to interact with students.